Okay, so the time is 6:05. Let's start the lecture. So first I'll start with my introduction. My name is Harini. I'm a PhD scholar at Interdisciplinary Center for Water Research at Indian Institute of Science, Bangalore. So I'm doing a PMRF TA duty for Watershed Hydrology course that is offered by Professor Rajendra Singh from IIT Kharagpur. Um, so now coming to So now coming to first of all, what do you mean by watershed? So first I'll start with the definition of watershed. So sorry for my writing. Um, so watershed is defined as an area of land that drains water from all the stream networks to a single outlet point. As you can see in the figure, the water from all these streams uh, are getting drained to the single outlet point that is here. So this is our outlet of the watershed, and we consider this part of the area as watershed. So now coming to the hydrology definition. So hydrology is obtained from a Greek word where hydro means water and logy means study. So basically, hydrology deals with the study of water. So coming to the formal definition of hydrology, hydrology means the science dealing with occurrence, circulation, distribution, and properties of water of the earth and atmosphere. So this course is called as Watershed Hydrology, where we will be studying about the occurrence, circulation, distribution, and properties of the water that will happen within a watershed. So now coming to the main important point of watershed hydrology is the hydrological cycle. So hydrological cycle involves all the hydrological processes that are going on within a watershed. As you can see here, uh, precipitation is a hydrological process from where water from clouds are uh, coming down onto the earth's surface in the form of precipitation. And the water that falls on the land is getting drained into the ocean as surface runoff, and the whatever water is falling on the earth's surface is getting stored in the depressions, which further gets infiltrated into the soil. As infiltration occurs, the groundwater also get recharged, and the water recharged in the groundwater will be discharged into the oceans uh, in long term process. And whatever water that is getting drained into the ocean will get evaporated back and form clouds. So the major important processes that are involved in hydrological cycle are precipitation, evaporation, and surface runoff, and infiltration, also groundwater recharge and discharge. Also, we have evapotranspiration. So, the difference between evaporation and evapotranspiration is that the water from the land surface as well as the plants together is considered as evapotranspiration. So, these about these processes we will be studying in future, but in this week we are concentrating on precipitation. So, what is precipitation? Precipitation is defined as any form of water, liquid, or solid that falls from atmosphere to the land surface. There are different forms of precipitation. So, one of the major form that we experience is rainfall. In case of rainfall, the drop size of the water will be of 0.5 to 6 mm. And we have one more important form of precipitation, that is fall. Then we have hailstorm. I'm not going into the definitions of this because it was already discussed in the lecture. And then drizzle, then dew, frost, sleet. So the daily section, the TA hours are being done on Monday and Tuesday from 6 to 8 p.m. Daily sessions are not available. And glaze. You can ask questions during these sessions. Okay. So now in our lecture, most probably we will focusing mainly on rainfall because that's the major form of precipitation that we experience within India. So coming to rainfall, based on the amount of rainfall that we receive, we have light rain, moderate rain, and heavy rain. So when you are trying to measure rainfall, we measure in units of depth. Like rainfall depth is 10 mm, 20 mm, like that. Or we will say that we are receiving a rainfall of 10 mm per hour. So that means 10 mm of rainfall occurred in an hour. That is the representation of intensity. So actually, the video that we are making now will be recorded and we will be posting on the YouTube as well. So you can check there as well. Or now, if you have any questions, you can ask us directly so that we can give you answers. Or you can mail as well. So rainfall is measured in depth, that units are mm, and also intensity, as I have discussed. The units will be mostly mm per hour we consider. Okay. So when do you say that rain is light rain? When the intensity of rainfall is less than 2.5 mm per hour, and we call it moderate rain when the intensity is 2.5 to 7.5 mm per hour, and it's a heavy rain when the rainfall amount is greater than 7.5 mm per hour. Okay. So also we are now recently experiencing events like cloud burst where we receive high amount of rainfall in a very short duration. Like we are receiving 100 mm per hour amount of rainfall in a cloud burst events. So now let's discuss about the basic questions that are related to this topic. Uh, Basically, I have talked about what is watershed, what is hydrology, watershed hydrology, and also the processes involved in hydrological cycle. Also, the forms of precipitation and how do you classify rainfall as light rainfall, moderate rainfall, and heavy rainfall. Okay. So the first question is which of the following processes is a key component of hydrological cycle? So first option is photosynthesis, second option evaporation, third option cellular respiration, and fourth option is mitosis. So as we have discussed that the hydrological cycle, yeah, the answer is evaporation. So hydrological cycle has precipitation, evaporation, evapotranspiration, surface runoff, also infiltration, groundwater recharge, etc. So the answer is evaporation. So the type of precipitation, the second question is type of precipitation that forms A smooth, clear coating of ice on exposed object is called snow. Someone has replied option snow, but it's wrong. No, snow. Snow when it falls from the atmosphere in snow form, right? So we are talking about the rainfall, the precipitation event where water drops form, and when exposed to the objects, a thin coat of ice will be formed. So answer is glaze. Maybe you can refer to the lectures to understand what does sleet mean, glaze, drizzle, and snow events. So rainfall of 6 mm is classified as light rain, moderate rain, heavy rain. Option D is none. Any answers? Yeah, the answer is moderate rain. Okay. Now let's discuss about more about how rainfall events occur and what are the types of rainfall events that are going to happen. So So basically, we receive rainfall due to uh, three modes because of three modes. Like there are cyclonic rainfall events, convective rainfall events, and orographic rainfall events. So first one we will talk about cyclonic rainfall. So basically, why how cyclonic rainfall occur is because of the counterclockwise rotation of air mass. Low pressure will be developed at the center, and this will pull all the wind and air to the center. So after that, the wind will raise up. The temperature of it will reduce and form clouds. Yes, yeah, you can ask question. Someone raised a hand. Hello. There is no question. I will continue. So when once the wind rises to higher altitude, it will cool down and form clouds, and then the water will fall as precipitation. So now I'll write the definition. So the second type of rainfall we are talking about is convective rainfall. When when hot air mass rises up, it will cool down and condenses, which results in rainfall. This is convective rainfall. And the third way is orographic rainfall. This will happen because of any barrier that the air mass is facing. So because of the barrier, the rain air mass will move above the barrier, and due to the altitude, because of reduction in temperature, the air mass condenses and results in rainfall. So in all the three cases, we can see that the air mass is getting lifted up, and due to high altitudes, the air mass is condensing, which is resulting in rainfall. This is the basic phenomena that is causing rainfall in our place. Okay. So now we will talk about how, uh, now we will just discuss about the questions related to this topic. So, the question is, what is the term for rainfall that occurs when warm, moist air mass rises, cools, and condenses, often resulting in thunderstorms? So, first option is cyclonic rainfall, second option, orographic rainfall, third option is convective rainfall, and fourth option is frontal rainfall. Any answers? So, the answer is convective rainfall. And the next, okay. So now let's discuss about the how do we measure the rainfall. So to measure rainfall, we generally use rain gauges. So in when we are using rain gauges, there are two types of rain gauges basically. So one is non-recording. So that means the data of it is not stored. We have to go there to the rain gauge and collect the data. Okay. Another one is recording. So in the recording rain gauges, the data will be stored in the instrument. So every day we will go and just get the data from the rain gauge. So the example for non-recording rain gauge is Simon's rain gauge. So this is our non-recording rain gauge. And all the remaining three examples that I have shown here are recording type of rain gauges. So here you can see that the first example is siphon rain gauge, where as the water keeps filling because of rain, the water depth increases, and this object will keep floating on the water, and it will keep taking the record. So here the accumulated rainfall depth is measured in this case. So now coming to the second example, tipping bucket. As you can see here, this silver triangular one, the rainfall will fall into that, and as the water keeps getting accumulated, and on the other side there won't be any water. So when this side gets full, it will drop down, and the water will keep accumulating on the other side. So that's why it is called as tipping bucket rain gauges. And the third example is weighing bucket rain gauges, where based on the weight of the water that is collected, we will get the measurements of rainfall. Okay. So suppose like when we have instruments on how to measure the rainfall using rain gauges, but how do you know how many rain gauges should be installed in an area? So To talk about that, we will talk about rain gauge network, which gives us an idea of the number of rain gauges within an area. Okay, so for this, we have a basic to find optimum number of rain gauges within an area. We find using a formula n equal to CV by error whole square. So this E represents the allowable error and CV is the quotient of variation of rainfall in existing rain gauges. So we already have some small n number of rain gauges, but we want to know whether that is sufficient or not. We will just find first what are the optimum number of rain gauges that are required for an area. Using this formula n equal to CV by error whole square. Okay, how do we calculate quotient of variation, standard deviation by mean of the precipitation values that are recorded in the remaining rain gauges into 100. So I think most of you know how we will calculate standard deviation, that is sigma pi minus p bar whole square by m minus 1. P bar is average of the precipitation at that station. Okay. So also there are other methods to measure rainfall, like we are using radars also while we are measuring rainfall. For India, we have IMD's Doppler weather radar system to measure the rainfall measurements. So in that radars, what we will be doing is we will be sending some energy signal, and based on the reflectance that is received, we have a relationship between the reflectance and the amount of rainfall, and using that we will predict what is the rainfall amount that happened in that area. Okay, other than rain gauges, we also measure rainfall using radars. Now we are also using satellites to measure rainfall. So coming to rainfall data, so we know how we are measuring, but how can you get rainfall data? So IMD is providing, India Meteorological Department is providing us rainfall data at a gridded level of 0.25 by 0.25 degrees, and which can be accessed from their portal directly. Also, you have station data, but that's not open source data. And there are other observed rainfall data sources like TRMM and GPM. Also, we can get ensemble precipitation data from MSWEB. So now let's look into few more questions. So the next question is, which of the following is a non-recording type of rain gauge? First option is weighing bucket type, tipping bucket type, and third option is floating or a natural siphon type rain gauge. Fourth option is Simon's rain gauge. Yeah, the answer is D, Simon's rain gauge. So the next question is, which of the following term is not used to designate a rain gauge? Pluviometer, ombrometer, hydrometer, and anemometer. Any idea or any guesses? So the answer is anemometer. Anemometer is used to measure wind velocity, and pluvial is another word for rainfall. Ombrometer and hydrometer both are designated for rain gauges. So the next question is, which one of the following points should be kept in mind while selecting the site for a rain gauge station? So option one, the site where a rain gauge is set up should be close to a meteorological observatory. Option two, the rain gauge should be on the top of a hill. Option three, a fence, if erected to protect the rain gauge from cattle, etc., should be located within twice the height of a fence. And option D is the distance between the rain gauges and the nearest object should be at least twice the height of the object. Yeah, the answer is option D. The distance between the rain gauge and the nearest object should be at least twice the height of the object. So, so the next question is rain gauge density is defined as the ratio of option A, total number of rain gauges in a catchment to the total area of catchment. Option B is total area of catchment to the total number of rain gauges in a catchment. Option C is total area in a catchment to the total area of the catchment. Option D is total area of the catchment to the total rainfall in a catchment. So, any guesses? I didn't discuss about this definition, but any guesses? Option A. But the answer is option B. The rain gauge density is defined as the total area of catchment to the total number of rain gauges within the catchment. So we will divide the total area by number of rain gauges in the catchment to get rain gauge density. So the next question is, which of the following is an advantage of using satellite estimates of precipitation? First option is high spatial resolution. Second option is real-time monitoring. Third option is ability to cover ground level rainfall directly. And fourth option is insensitive to cloud cover. So the answer for this question is we'll get high spatial resolution of data. So when there is a cloud cover, we cannot acquire data using satellite, and also we cannot get ground level data, and the real time monitoring is not done because the satellites revolve around the earth, so it's not easy to get real time monitoring of rainfall data. So now that we have the rainfall data with us, so how do you want to visualize the data? And we want to know whether there is a consistency or inconsistency in the data. Okay. So for basically visualization, we have three methods that were discussed. First one is mass curve. So where we plot cumulative rainfall depth versus time. Okay. So what is cumulative depth? So we have, suppose we have rainfall data like this: time, rainfall. So in 1 hour, we have some 2 mm of rainfall. In 2 hours, we have 0.5 mm. And in the second hour, we have 0.5 mm. In third hour, we have 1.5 mm. So the cumulative rainfall will be in first hour, we have 2 mm. In total second hours, how much amount of rainfall happened? So we will add all these two to get 2.5. So we say 2.5 mm of rainfall occurred in 2 hours. So to find cumulative error in 3 hours, we will add all these three values. So that means 4 mm of rainfall. So the time versus cumulative depth is plotted to get mass curve. So next one is hydrograph. So in case of hydrograph, we have it's a bar diagram which is plotted between rainfall intensity and time. Okay. So what is rainfall intensity? As I have discussed, we will find how much amount of rainfall occurred in a fixed interval of time. Okay. Suppose here we have the time units with a interval of 1 hour. So when we know that in first hour 2 mm of rainfall occurred, then the intensity will be 2 mm per hour. Okay. In the second hour, we know that 0.5 mm of rainfall occurred. That means from the end of first hour to second hour, we have a 0.5 mm of rainfall. That means the intensity is 0.5 mm by its 1 hour duration. So it's 0.5 mm per hour. And in third hour, we know that 1.5 mm of rainfall occurred. So in the duration of like from the end of second hour to third hour, we have 1.5 mm of rainfall occurred in a duration of 1 hour. So it's the intensity is 1.5 mm per hour. So when we have the plot, it's rainfall intensity per time. So each bar will be a representation of intensity, and the area of the bar will account to amount of rainfall occurred in that hour. So if you multiply this 1.5 into here, the thickness of the bar will be 1 hour, right? So when I multiply with 1, that means it is 1.5 mm. So 1.5 mm amount of rainfall occurred in this particular hour, right? So the third way to visualize the rainfall data is depth area duration curve. Okay, so here we have a plot between average rainfall depth in mm or centimeters, anything is fine, and the x-axis will be area, mostly in kilometer square we consider, and each line corresponding to the duration. That means the duration means the time interval for how long the rainfall event occurred is called as duration. So 6 hours, maybe 3 hours, 1 hour. Okay, so that means, okay, so this curve will talk about the amount of rainfall. This curve gives us an idea about the depth of rainfall that occurred in 1 hour duration. that can occur in 1 hour duration at different areal scales. So suppose here we have this represent 10 kilometer square and this is 50 kilometer square. So this is the average rainfall depth that has occurred in 1 hour duration within 10 kilometer square of area. Okay, so this will represent as the this will give us the amount of rainfall, that is the average rainfall depth that occurred in 1 hour duration uh, in an areal extent of 50 kilometers square. So similarly, if you go for other duration curves, so this will give us, suppose it's like 30 kilometers square. Here we will obtain the rainfall average rainfall depth for 6 hour duration that can occur within an area of 30 kilometers square. Okay. So generally for this curves, we have a relationship that was defined P bar equal to P naught into e power minus k into a power n. Okay. So where here k and n are constants and P naught is the highest rainfall amount in the storm center. Okay, and P bar represents the average rainfall depth. A is the area. Okay, so using these equations, generally we will try to using the observed data, we'll try to fit equation and find the constants like k and n, and then we will plot the curves. Okay. So now let's talk about inconsistency in the rainfall data. So why do you think the inconsistency in the rainfall data that can occur? So if the rain gauge was fixed in one position and the location of it is changed, then the amount of rainfall that is recorded will be changing. So you can see that there is no consistency in the rainfall data when you plot the time series. So, and also one more reason is that if you change the instrument itself, suppose if from recording to non-recording rain gauge to you go for recording rain gauge, and also like when the environment of the surroundings is changed, like before there was it was a forest area and now it's converted to agriculture plant, so there will be some inconsistency in the data that we will observe due to this reason. So to address this inconsistency, we will try to check the inconsistency in the rainfall data using double mask curve. So in the double mask curve method, what we will be doing is we will plot a curve between cumulative annual rainfall of the station X, and on the x-axis we will be plotting cumulative annual rainfall of the neighboring stations. Okay, so first, whatever data that is available, we will arrange in a reverse chronological order and then find cumulative rainfall at a particular station where we are checking if there is any inconsistency in the data or not. And also we will find cumulative rainfall, annual rainfall, using all the remaining neighboring stations. Okay. And then we plot the graph. So initially, if we got a plot like this, that means there is an inconsistency in the data. If suppose the plot is like this, then it means that it is a consistent data. So when you see this, when the line is exactly at 45 degrees angle, then the data is consistent. Okay. So if there is inconsistent data, what do you have to do? We will correct the data set. So for that, we will be using a formula of correction factor. Suppose this line is called as O, E, this is C. I'm defining point names. Okay. So the correction factor is slope of OA divided by slope of AC. Okay. So from the x and y values, we can find the slope of line OA. And suppose here we have A and B. Using that, we can find the slopes for the line AC. So for slope of OA is equal to y by x. Slope of AC equal to P by A. So once you find the slopes, you will substitute into the correction factor and we will calculate the correction factor. Then whatever the observed data is there, we will multiply it with the correction factor and find the exact accurate rainfall data. Okay. So now let's look into a few of the questions. So the first question is, the mass curve of rainfall is a plot of, first option, intensity of rainfall against time, second option, precipitation against time, third option, cumulative precipitation against time, fourth option is flow rate against time. Yes, the answer is C. Accumulated or cumulated means the same. Accumulated precipitation against time. So now here I am trying to show an example how to develop the mass curve and hydrograph from a given data set. So here we have rainfall values given at each hour. So in first hour we have 0.5 centimeters of rainfall, and in second hour we have 1.5 mm of 1.2 centimeters of rainfall. So first for mass curve, the curve is between cumulated rainfall versus time. So we will find first cumulated rainfall. So for how do we find cumulated rainfall? So for first hour it is 0.5. In second hour, we'll try to find the total amount of rainfall that occurred in both first and second hour. Okay. So it's 0.5 plus 1.2, that is 1.7. And in 3 hours, we have a, let me get cancel. So in 3 hours, we will add up the first three values, 0.5 plus 0.1.2 plus 0.8. So that is 2.5 centimeters. Then we have fourth hour, we have zero rainfall. So it is still 2.5. Fifth hour, we have 1.5 centimeters. So we will add up all these values. Then the rainfall amount will be 4. So go on like that. 11.8, 16.4. So now when I'm plotting it, when I'm plotting the mass curve, cumulative depth in centimeters versus time, right? It is in hours. So be sure to mention the labels, units of the labels of x and y every time whenever you are plotting. So in first hour, it is 0.5. I'm just randomly drawing it. Second hour, 1.7. Third hour, 2.5. Then again, fourth hour, it's 2.5 again. Fifth hour, 4. So like this, when you try to connect the curve, whatever we get is a mass curve. So as you can see that mass curve is always a non-decreasing function. It will be either increasing or it will be remaining constant. Okay. So hydrograph, how do you plot a hydrograph? It is rainfall intensity versus time. So now we will find rainfall intensity, which units are centimeters per hour, right? So since the interval is 1 hour duration, so whatever the rainfall will be our rainfall intensity. It is first value is first one is 0.5 divided by, since it's a 1 hour duration, 0.5 by 1, it will be 0.5. Second hour, we have 1.2 uh, centimeters of rainfall in 1 hour duration. So the intensity will be 1.2 centimeter per hour. Third hour 0.8, fourth hour 6, 0. Similarly, like this, if we keep going on, these are the values that we will be getting. So now when I plot it, so hydrograph is a bar plot. So between rainfall intensity, centimeters per hour, and time in hour, right? So in first hour, we have 0.5 centimeters per hour. In second hour, we have 1.2. In third hour, it's a box plot, right? Sorry. We have 0.8. And in fourth hour, it's a 0 value. Fifth hour, it's 1.5. So like that, if we keep going on, we'll get a hydrograph for the rainfall data. So as you can see that here, the bar plot won't be like non-decreasing or anything. The fluctuations are clearly visible. Okay. So now let's go more into theory part again. So now that we know that um, how we will get rainfall and how do we measure the rainfall in a particular place, and what are the optimum number of rain gauges that are required for a given area. And once you obtain rainfall data from either IMD or any other source, once we have an observed rainfall data, we know how to visualize the rainfall data, and also to check, and also we can check how whether there is a consistency or inconsistency in the rainfall data. Now that we have the observed rainfall data for the area, to get an generalized information about the whole basin or watershed, we will try to estimate mean annual rainfall. Sorry. So how do we do that? We have four methods, I think, discussed in the presentation. So first one is, arithmetic average method. Okay. So when do we use arithmetic average method? Since we have like multiple methods to calculate mean annual rainfall, when do we use arithmetic average method? Any idea? So the answer for that is when the catchment is hydrologically homogeneous. That means like the rainfall amount doesn't, the rainfall that the catchment received doesn't change spatially, or the temperature or any other hydrological processes that are happening within the catchment doesn't change spatially, then we call it as hydrologically homogeneous catchment. And when the rain gauges are uniformly distributed, then we apply this arithmetic average method. Okay. So since for this particular catchment, we have rainfall data at these points. The rainfall data at these points is called point rainfall. And using this, if the catchment has hydrologically homogeneous and if the rain gauges are uniformly distributed, to calculate areal mean rainfall, we will use arithmetic average. And the formula for that is P bar equal to, so I have 1, 2, 3, 4, so on, like n stations. Sigma of I equal to 1 to n, Pi by n. Okay. So that's how we will get the areal mean annual rainfall values using arithmetic average method. So the next method is Thiessen polygon method. So in practical, the hydrology for any catchment, the hydrological behavior won't be homogeneous, and we won't have rain gauges uniformly distributed because of the topography. Suppose in areas like mountainous areas where people cannot reach there, we don't have rain gauges. So that's why we go for methods like Thiessen polygon or isohydral method, where we will put some weights on the observed rainfall data at each point. Okay. So suppose we have a catchment like this, and we have rainfall data at point A, B, C, and D. So first thing that we do in Thiessen polygon method is we will join the each stations, okay, by a straight line. And now calculate the draw the perpendicular bisector for the lines that are joining the stations. Okay. And this perpendicular bisector will give us the area that is contributing for this particular station C. That means C has more influence on the whatever rainfall data that is recorded at C station is more accurate for this area. And similarly, we can find the areas of each section. Okay. AB, suppose this is area AB, AC, AD, and AA. Now when we are trying to calculate the spatial average, so it will be precipitation at station A into area at station A, area contributing for station A, station B, area at station B divided by total area. Okay, so in simplified manner, I equal to 1 to n pi ai by area. So this area you will generally calculate using like planimeter or any graphical sheets. You will try to estimate the area that are influencing for each station. Okay, the next method is uh, estimate uh, areal mean annual rainfall. It is isohydral method. Okay, so suppose for a catchment we have isoheights. So what does isoheight means? So isoheight is a curve that gives an idea of the amount of rainfall that has occurred. Okay, suppose if I am saying that this is 10 mm rainfall isoheight, 20 mm, 30 mm, 40 mm. That means over this entire curve, the rainfall amount is 10 mm. That is observed. So in this area, in this curve, on this curve, it's 20 mm. Like it's like a contour. So for elevations, we have elevation contours where the contour will represent the elevation of that area. Using the joining the same elevation points, we will get a contour. So this is a contour for rainfall depth. Okay. So now that we have the ISO heights, then what we will do is we have the rainfall value. Suppose this is R1, R2, R3, R4, and so here we have R0 and R5. And suppose here we have a rainfall. Suppose this area is A1, A2, A3, A4, A5. Then what we will do is to calculate the average rainfall. So first we will take mean of R0 plus mean of R1 and R2. So we will say R1 plus R2 by R0 plus R1 by 2 amount of rainfall occurred in an area of A1. So like this. So we'll take averages and then we'll multiply with the area between the contours. So on divided by total area. So based on the area that lies between the contours, we will assign weights for each isoheight. Okay. So this part is clear, right? Okay. Any questions? Okay. Now we'll go for another method called two-axis method. Okay. So in this, I'll give you a brief idea of what we will do. So suppose if we have a um catchment, first we will try to delineate the catchment and also we will find the outlet. Suppose this is the outlet point. Okay. And we will find the farthest point from this outlet. So suppose this is our farthest point. First, let's join these two points, outlet and the farthest point, and draw a perpendicular bisector to it. So this is our minor axis. As the name suggests, we have two axes. First one, we have now defined the minor axis. And now to this minor axis, draw a perpendicular bisector. Suppose this is my perpendicular bisector, then this is major axis. Okay. Now we have defined the two axes. Okay. So now suppose we have a station here. Suppose this is called P1. We will try to join P1 to a point on these axes, which is the farthest point. Suppose for this label, we are labeling this major axis as AB and minor axis as CD. So the farthest point from P1, which lies on the major axis, will be A. So first I'll join this. Similarly, I'll join the farthest point on the minor axis to the station P1. Okay, that is D. So now that we have joined, we can find the angle that is made by this two lines. Okay. So since we know the locations of A, B, C, D and also the location of the station, we can calculate the distances, right? So P1, A, B. Okay. And this is our theta. Okay. So suppose distances are A, B and C, then we can calculate from cos inverse equation that theta is equal to b square plus c square minus a square by 2bc. Okay. And based on this, we will calculate A weights. Okay. Weights are equal to theta I by sigma of theta I for all I. And the rainfall, average rainfall is calculated as sigma of I Wi into Ra. Okay. Is this clear? I know it's little congested. Is this two axis method clear for everyone? I hope it is clear. So basically in this two axis method, what we are trying to do is we will assign more weights to the stations that are closer to the station where we are trying to estimate. Okay. And also we will assign more weightage to the central point of stations. Okay. Now let's go for some questions. So the first question is, which of the following methods is commonly used to estimate mean annual rainfall for a region? So first option is radar based estimation, or second option is ground based rain gauge station, third option is satellite observation, fourth option is all the above. Any answers? So basically we get the observed data from all the three ways, like satellite, ground based, like using rain gauges and also using radar. So whatever the data sets we are getting, irrespective of the source, we can calculate mean areal rainfall. So the option is all of the above. So the next question is, in the decent polygon method, how are weights assigned to each rain gauge station? First option is based on elevation. Second option is proportion to the station's area. Third option is inversely proportional to distance. Fourth option is randomly assigned. So as I have discussed in Thiessen polygon method, we'll try to calculate the amount of area uh, that is more influenced by the station, right? So that means we are assigning weights based on the proportion to the station areas. So now let's solve a problem. So the problem is for a catchment of monthly rainfall and the corresponding Thies and polygon weights for the station are given below. Use Thies and polygon method to get average precipitation over the entire catchment. So here in the question, the Thies and polygon weights are given, not the area specific to the station, right? So each weight is corresponding to AI by A. That means station's area divided by total area. This is called as weight in this case. So from the formula of Thiessen polygon, we know that P bar equal to sigma of I, Pi, Ai by total area. This can be written as sigma of I, Pi into Ai by A. Okay, this is our weights in this case. So it's sigma I Pi into Wi. Okay, now let's try to substitute the given data. So first station we have 28 into 0.05, 22 into. Okay. So I'll use calculator for this. So the answer is 32.66 centimeters. So the areal average precipitation over the catchment will be 32.66. So the answer also should be in between 32 to 33. The next question is, an isohyet is the line joining equal option 1 depth of rainfall, option B time of concentration, option C is rainfall intensity, option D is none of the above. Any cases? Yeah, option A. Option A, rainfall depth. So now coming to second question, next question. The isohyets for the monthly rainfall over a catchment is given below. So now we have to calculate the areal average precipitation over the catchment using isohyetal method. So first thing from the data we can see that isohyet interval is given and also the area between the isohyets. Here in this picture we can assume that this is 0 in case, and also somewhere around here we have a 60 mm of rainfall isohyet. Okay, so now they have given the area that falls in between 0 to 10 mm of rainfall isohyets within the catchment. Okay, so this is the area of the catchment that lies between 10 to 20 mm of uh, rainfall depth isohyets. Okay, so now first thing is we will calculate the average isohyet. Okay, so average isohyet is calculated like minimum and maximum of the interval by 2. Okay, So that is 5. So this will be 10 plus 20 by 2, 15. Similarly, it is 25 mm, 35 mm, 45 mm, 55 mm. So I can show the clear calculations for one or two. So once we have the average ISO heights, what we will be doing is to calculate the P average. We'll multiply this average hydrogram ISO height with the area. So 5 into 10. For 15 mm it is 25 kilometers. 25 mm, 35. For 35 mm it is 45 kilometers plus 45 into 20 plus 50, 15 by total area. Okay, so I've used calculator for this. Here also the units are mm. Okay, so the average areal precipitation over the catchment using isohydral method will be 30.67 mm. Okay. Now that we know that the rain gauges etc. are used for measuring the rainfall data, we know that any observed data we will face a missing gaps. So why do you think we have missing gaps? Maybe because the on that period of time there is no one to collect the data from the rain gauges, or when you are going for satellite observation due to cloud cover we cannot get the rainfall data. So in these cases we will have missing gaps. So to fill these gaps in the rainfall data we have a few methods. So first method is arithmetic average method. So in this what we will be doing is, um, suppose in a catchment we have n rain gauges, and at one station, suppose this station, we have missing data. Okay, so what we will try to do is, using the neighboring stations, we will try to fill the gaps in this missing station. We will find, will fill the gaps in this station X. Okay, which has missing data. So the formula will be Rx equal to 1 by n. Just we will take a arithmetic average of it, and we will find the arithmetic average. So, and the next method is using normal ratio method. So in this case, what we will try to do is we will estimate a normal rainfall. So what is normal rainfall? At every station, what we will do is we'll find the average, long-term average of rainfall data at each station. That is called as uh, normal rainfall. So generally we will take for 30 years or more. So once we take the average for a 30 years period, the rainfall amount is called as normal rainfall. So when the normal rainfall so of station X is calculated, and if we find 10% of Nx, so when we find these two values, if all the station normal average, all the normal rainfall values of the remaining neighbors lies in this specific range, then we will apply arithmetic average method. If the normal averages of all these neighboring rainfall station, rain gauge stations doesn't lie within this particular range of 10% variation of station X, then we will go with the normal ratio method. Okay. So for that, the equation is Rx equal to, since I have taken station numbers as 1, 2, 3, let me write it like that. We have n neighbor stations, and this R bars represents the normal rainfall, and normal R represents the point rainfall data. And that is rainfall occurred in a particular time step, okay, at a particular station. So here we have R1 means the point rainfall at station 1, and R1 bar means normal rainfall at station 1. So normal rainfall, as I have told, we will take the average for a long term period, that is for 30 years. For 30 years of rainfall data for station 1 is obtained and take an average, then we will get normal rainfall for station 1. So next we have inverse distance weighting method. Okay, so here what we will be doing is we have n neighboring stations. So we will assign some weights on to this each station. These weights are assigned based on the distance. So suppose from the station X, what is the distance between the station I? Based on this distance, we will assign some weight for this station. And based on the distance between station X and some station J, we will find the weight for that particular station and calculate the value so that we can fill these missing gaps. So how do we calculate weights for each station is, suppose for station I, the weight will be 1 by di square. So how do we calculate di is the distance between station I and station X. So since we know the coordinates of these stations, we can find the distances between the station and find the weights by inversing them. Okay. So then what we will do is we will calculate the rainfall at X using these weights. So if these weights are not 1, that's why we have this denominator in the down, so that we will make the sum of all these values to 1. Okay. So now coming to a problem, we have normal annual rainfall of 5 gauge stations given in the table, and for a particular year we can see that, sorry, station 2. For station 2, the rainfall data is missing. So now we will try to calculate the missing value using normal ratio method or any other method, and also we have to give a reason why we are using, if we are using normal ratio method. Okay, so first we have, suppose this is our station where the data is missing. So n of A2 is given as 110 centimeters, right? So 10% of this is 11 centimeters. Huh? So now we will find a 10% interval range. So that is 110 minus 11. 99 and 110 plus 11, 121. Okay, now try to check if all these values, all the normal rainfall values for the stations A1, A3, A4, A5 are within this range of 99 to 121. So we can see that this station's normal rainfall, this station normal rainfall, this one also, it's not within the range of 99 to 121 mm. Okay. Hence, we will go for normal ratio method. So now, as I have discussed earlier, how do you find value? How do you fill the gap using a normal ratio method? The formula is so now let's substitute the values 110. We have 1, 2, 3, 4, 4 neighboring stations by 120. So the value will be equals 10 meters. So using the calculator, I found the uh, missing value, and that value is 10.85 centimeters using normal ratio method. Okay. So now we have one more question where we will try to find the missing value at rain gauge station A4 using inverse distance method. So as I have discussed, like we will know the location of this station. So we have the coordinate values, x and y values for each station. Now first thing is we'll try to find the weights. So first one is we'll find the distance between station 1 and station 4. That is square root of 0 minus 3 whole square, 0 minus 2 whole square. So this is Euclidean distance formula. That is, if the coordinates of two stations are x1, x2 and x1, y1 and x2, y2, then we will find the distance between stations using this formula. Okay. So this is, I'm not trying to get those values into decimal. So now I have this. So now first I'll assign the weights for calculate the weights, that is weight is defined as inverse square of distance, right? So for first one it is 1 by 13. So for second it is 1 by 2. For third station it is 1 by 2. So suppose now that if you see that for each station, if I add the weights W1 plus W2 plus W3, it's clearly more than 1, right? So for exact value is 1.07. So to normalize this, that's why we have a formula Rx equal to sigma of Ri into Wi for all values of I divided by Wi. This denominator is here to make sure that once there won't be extra weightage for the rainfall values. So now 1 by 13 into rainfall value at the first station is 35. Weightage of second station into rainfall at second station. Weightage of third station into rainfall of third station divided by sum of the weights. Okay. So the value is coming around 35.23 centimeter. So the missing value at station A4 will be 35.23 mm using inverse distance weightage method. Okay. Okay. Now let's go for the last topic of the of this week's lecture, that is frequency analysis. Now that you have all the observed data for the observed data at each location, we know how to get areal average, also how to, if there is any missing gaps, how to fill the data, and also we know how to check whether there is an inconsistency in the rainfall data or not. Okay, now with this rainfall data, what we will try to do is like we will try to do frequency analysis. That is like suppose we have a 100 mm of rainfall. It's a very huge amount of rainfall. We want to know how frequently will occur so that we can construct our infrastructure like water drainage systems or dams, etc. All other water resource structures based on this this information. Okay, so first thing, first thing is the frequency analysis. What does it deal with? As I have told, it deals with the chance of occurrence of an event. Okay, of an event, chance of occurrence of an event with the magnitude of. We will specify the magnitude. Okay, so definition is event with chance of occurrence of event with magnitude greater than or equal to specified magnitude. Okay. So in this case, what we will do is we will assume that the data that is available for us is independent and also identically distributed. Also for the hydrological system, we will assume that it is stochastic and spatially and time independent. Okay. So the basic things that that we deal with the frequency analysis is first we'll try to find the probability. Okay. So here, how do we define the term P? So it is defined as probability of occurrence of an event X whose magnitude is greater than or equal to a specified magnitude. Suppose we'll say XT. Okay. This is termed as probability of exceedance. Okay. And we will write it like, okay. For this, we can give an example of probability of x greater than or equal to 150 mm of rainfall. Okay. And also we have few more terms like recurrence period or return period, which we will calculate as inverse of this probability of exceedance. Okay. So what does this return period represent? So return period represents the average interval that is required for the two events to occur successively with a magnitude of xt. So suppose we say, so I will say that suppose I'll give an example that the rainfall event of 150 mm for a duration of 2 hours will occur with a return period of let's say 100 years. So 150 mm rainfall of 2-hour duration occur with a return period. I'm defining RP as return period of 100 years. So this then we can say that at least once in there is a chance that in once in 100 years we will experience a rainfall event of magnitude 150 150 mm. Or also we can define that the time interval between this first 150 and second 150 mm of rainfall will be most likely that the gap will be of 100 years. Okay. So the next definition is probability of non-exceedance. That is P of x less than xt. That is equal to, since sum of entire probability is equal to 1, we can write it as 1 minus P of x greater than xt, right? So this will be 1 minus P. We generally write this as Q also. Okay. Now we have like few methods like how we will find the probability values. So suppose if we go for distributions like binomial distribution, in which case we try to find what is the probability of r occurrences in n successive years. Okay. So we know that how do we calculate the probability is NCR. We know probability of occurrence of an event as P power R Q power n minus R. An event. Okay. Also, we can go with empirical methods. So instead of going with the distributions, so what we will do is from the observed data itself, we will try to we will assign ranks to the observed data, and then we will find probability values. So I'll not write all the equations that are listed in the lecture given by sir, but I will mention one main formula, that is Abel's method. Okay. In this, what we will be doing is we'll find calculate probability based on the rank of the data, and capital N is the length of the data. Okay, suppose we have a time series of rainfall data. Suppose like at day 1 we have some 10 of rainfall, day 2 30 day 3 40 etc. like this for 1 year. Then we will assign rank 2 for each specific day. And when we divide the rank by total length of the data plus 1, we will get the probability of occurrence for each rainfall data. Okay. So, and also next we have frequency factor, where we will find like, basically it is represented like this. Suppose this is the frequency factor. X bar is the mean of the data and sigma is the standard deviation of the data. So for normal distribution, generally k value is 3, and for log normal other distribution, the k value is like we have a very long equations to find that. And so generally, so what we will be doing is using this equation based on the return period and the duration of the rainfall, we will have a k factor value. And using the mean and standard deviation of the data, we will find the return value, return level of the rainfall intensity. Okay. So the last we will be discussing about intensity, duration, and frequency curves. So to develop these kind of curves, we need at least like 20 years of data. And so we have a relationship between the intensity, duration, and frequency that is defined by the Kotiari and Garden. So for intensity value at duration t and return period capital T is defined as C into t power 0.2 by small t 0.71 into this is the rainfall value that occurs with a return period of 2 years and for a duration of 24 hours whole power 0.33. Okay, so here this C varies specially, which is also given in by them. Okay, so you can refer to that in the lecture that based on the location of it, the C value will change, and based on time, return period and time, we'll get the intensity value. So generally, the intensity, duration, frequency curves will be. So if I add one more slide, the IDF curves. Okay. Hmm. So the IDF curves will look like this: intensity, duration. As the duration increases, the intensity will decreases. The curve will be like this. And as the return periods increases, the intensity amount increases. Okay. So suppose this is for 50 years, this is for 20 years, 10 years, like that. So what do we understand from this? So suppose here we have a 1 hour duration rainfall. So we can see that for 1 hour duration rainfall with 10-year return period has an intensity of, suppose let's say 10 mm per hour. Okay. So if we go for same 1 hour duration and 50-year return period, the rainfall is around like 60 mm per hour. So that means as the return period is increasing, the rainfall intensity is increasing. Also, if we go for suppose 24-hour duration and 10-hour return period, the rainfall amount is suppose let's say 5 mm per hour. So as the duration is increasing, fixing the return period, the intensity values are decreasing. So based on these curves, what we will be doing is we will try to design the water resource structures based on the return periods that are obtained. Okay. Now let's solve the last two problems. So the first problem is the annual rainfall recorded at a station over the past 10 years is as follows. Compute the probability of exceedance for p x of x greater than or equal to 10. So now that here we have mentioned that we need to find a probability of rainfall greater than or equal to 100 mm. So let's first from the observed data, let's try to see how many times the rainfall has exceeded 100 mm. Okay. So 1, 2, 3, 4, 5, 6. Okay. So number of times rainfall is greater than 100 mm is 6. So total rainfall events is 10. We can see we have a 10 years of data, so it's 20. So then the probability of x greater than or equal to 100 is number of times rainfall exceeded 100 mm by total number of rainfall events. So it's 6 by 10, that is 0.6. Okay. So this is our answer. So the next question is, what is the probability that there would be 3 rainy days in a week, given that the probability of rainy day is 0.3. So as we have discussed in binomial distribution, we have mentioned that binomial distribution deals with r number of successes that have occurred in n number of trials, right? So suppose week has 7 days. So here we want to find a probability that there is a rainfall happening in 3 days. What is the probability of rainfall occurring in 3 days out of 7 days? Okay. So P of the number of successes should be 3 for us, right? So as we know, the formula is NCR P power R into Q power N minus R. Q is 1 minus P, right? So here R is 3 and the number of total number of the successes that trials will be 7, right? We have 7 days in a week. So N is 7, C 3, and the probability of a rainy day is 0.3. So P equal to 3 and R is 3. So using calculator, that is 0.227. So our answer is option A. So the probability of 3 rainy days in a week will be 0.227. So that's the end of the lecture. If you guys have any questions, you can ask me right now. Any questions? Okay. So then let's meet next week, same on Tuesday from 6 to 8 p.m. Mm, Thank you for listening.